Okay, here we'll pick up from the end of last class where we began the unit on work. So we had ended talking about when work is not done, and we looked at the weightlifter here, and holding 100 kilograms over your head is not considered work, and the reason why. We had said there's no movement resulting from the force, and the weight's only held in place. So as long as the weight is static, which means it doesn't move, then no work is considered to be done. Here, if Sheldon is applying 20 newtons in an attempt to open a jar but the lid won't move, we would still consider no work being done here because the lid has to move in order for work to be done. On the next example, a 200 kilogram puck is sliding across a smooth horizontal surface at 8.5 meters per second for a distance of 100 meters. Is work done in this case? And the answer will be, since no force is applied to the puck to cause it the movement and friction is low, no work is done because it continues without an applied force. So remember the conditions for work to occur. A force must be applied and the object must move in response to the force. So force is not applied to keep the puck moving, then no work is done. So remember, no force, no work. If the object moves and force is not applied, again, no work. And if the object doesn't move in response to the force, then no work is considered to be done. We can summarize work the following way. Work equals force times distance, and the force must be parallel to the direction of motion. So if I look back here, when the individual here would stand, we would consider work to be done. When the person stands up straight, the force applied is in the direction of motion, so work will be done. Alright. So work equals force, and the symbol here means parallel in the direction of motion, multiplied by the distance that you move. And remember, distance is always in meters. So the first example, a 25 Newton horizontal force is applied to a box and it moves 4.5 meters across the surface. How much work is done? Well, we have an applied force and it's in the direction of motion, and the box moves 4.5 meters. So in this case, work is force times distance, 25 newtons times 4.5 meters, works out to 112.5 Newton meters. Now we have a new symbol. Instead of keep saying work is in Newton meters, this unit used now is joules. So the answer here would round to 1.1 times 10 to the 2 joules. So what you need to remember is that 1 joule is 1 Newton meter. Joule is a unit of work. Now what happens if force is not in the direction of motion? From Unit 2 we looked at horizontal and vertical components of a force to act upon an object. So if someone here was shoveling snow and applying 200 newtons of force down the handle at 60 degrees to the horizontal, so 60 degrees to the ground, and the shovel moves 8.5 meters, how much work is applied? Well, first we need to find the force horizontal and find the horizontal component of the force. Remember, it's the force applied times cosine of theta, or 200 times cosine 60 degrees, and that should work out to give you 100 newtons. Now we know how much force is applied, so we can find the work. The work is force times distance, or 100 times 8.5, and we have 850 joules. Now we find that two previous formulas can be combined. We know that horizontal component of a force is the applied force times cosine of the angle, and we know work is force horizontal times distance. Well, we can do a quick substitution here. Force horizontal is force times cosine theta, so we substitute in here, and we have work is force times distance cosine of theta. Important for you to know that work is a scalar quantity. Work does not have a direction. Even though displacement and force are both vectors, the result is not a vector. Each was known as a dot product, and it will always result in a scalar quantity, so there will be no direction associated with it.